Thank you for the introduction. My topic is micro-indentation measurements on the well-bore cement, presented by Hui Du and Dr. Maliva Radonjic from Louisiana State University, Hawkins Department of Petroleum Engineering. Here's the outline of my presentation, including the motivation, objective, introduction, sample preparation, methodology and equipment, result, summary, and the future plans. Also the acknowledgements. Motivation. Wells provide us the access to the hydrocarbons beneath Earth's surface. And there are currently 1.8 million wells worldwide, and out of which 10% has cement-related problems. Also, the statistic from Gulf of Mexico shows that 58% of the incidents that lead to the loss of well control were linked to the cementing operation. So these facts brought our interest to the well-bore cement. And the objective of our research is to apply the micro-indentation test in evaluation of the well-bore cement integrity. Also, we are hoping to develop a correlation to protect the cement compressive strength through a non-destructive property, the indentation hardness. Introduction. Well-bore cement is the cement slurry placed in the annulus behind the case, as shown in the figure on the right. And the main objective is to provide zonal isolation and casing support, also the corrosive protection. The integrity of well-bore cement is a function of its mechanical properties. And the mechanical properties we are measuring here is the hardness and the Young's modulus through the indentation test. Also, we will do the compressive strength test in the near future. And since it is the most widely used cement strength parameter for the purpose of classification and design. And hopefully we can come up with a correlation about the result from the indentation test and the compressive strength test. And so that the compressive strength can be predicted without destruct the sample. Sample preparation. This picture shows the key factors of a cement design, including the cement type, the water to cement ratio, water salinity, chemical additives, the mixing procedure, and the time for the hydration. So in our experiment, we use the same type of cement and go through the same mixing procedure and given the sample same amount of time for the hydration. So which makes the top three parameter as the constant and leave the bottom three parameter as the variables. The samples were made with different water to cement ratio and different water salinity, also different chemical additives. On the right is the schematic of the indenter equipment. Can I use a pointer? The indenter with the diamond tip was driving into the sample with the increasing normal load. During the same time, the position of the indenter relative to the sample surface was recorded by a non-contact displacement sensor right here. The picture on the top is a sample of the cement we made. It was cut into 1-inch diameter cylinder with a thickness about 1 inch. Also polished the bottom and the top to make the surface parallel and soaked in high pH water before the test. On the bottom is an example of the indentation line. You can see here with the dots. And typically 8 to 12 points was chosen to do the indentation test for each single sample. The last picture here is an example of the indentation surface of a single mark. And the legend here is 0.25 millimeter. Here's our result. Cement with different water-cement ratio. As the figure shows, as the water cement ratio increase, both of the hardness, the blue bar, and the Young's modulus, the red line, decrease. This is because the excess water that is not consumed by the hydration reaction leaves the cement microscopic pores. And SEM picture was used to compare the difference. You can see here is the 0.4 water cement ratio, here is the 0.9 water cement ratio. And for the 0.4 sample, it appears to be more dense and the whole texture is well compact. Well, on the 0.9 water to cement ratio, it shows visible porosity. The last picture here is the compressive strength of cement with different water cement ratio done by T.R. Knight in 1992. And we can see the compressive stress actually have the same trend of the hardness. As the water cement ratio increased from 0.4 to 0.6, the compressive strength reduced more than 50%, while the hardness reduced about 60%. We are expecting the hardness and the compressive strength can be correlated after we measure our own compressive strength on the samples. Here's more result. On the left is the cement with different water salinity. You can see in the figure as the water salinity increase, both of the Young's modulus and the hardness decrease. This is most likely because the salt inside the cement attracts moisture. And on the right is the cement sample with different additives, including a knee cement, silica sand, steel fiber, glass fiber, and calcium clay. As you can see, after we adding additive to the cement, the hardness actually drops no matter what you add. And this is because the material you add into the cement is never perfectly bound with the cement. And well, the Young's modulus for red depends on the material you add. Also, one more thing to notice here is the standard deviation for the additive cement is much higher than the knee cement. This is because when we do the indentation, when the indenter touch the cement surface, when it touch the cement and it touch the material you added, you get a highly deviated value. This is why we have a high standard deviation right here. Summary. So water to cement ratio is a dominant factor on mechanical property of the cement-based material, and high water to cement ratio yields lower hardness and Young's modulus, as well as the compressive strength. Also, using salt water will significantly decrease the mechanical properties of cement. And also, as water salinity increase, both hardness and the Young's modulus drops. Additive have a significant effect on both hardness and Young's modulus. Our future plan is to conduct the compressive strength test with the same cement design and correlate the compressive strength with the indentation result. Hopefully, we can predict the compressive strength with a more efficient method. It's an acknowledgement. That's it. Thank you.
We have some time for questions. All right.
So, what cement water ratios do they use in industry, and how does that compare with your?
Well, there was a minimum amount of compressive strength. I think it's 5 megapascal, and if you can see on my slides. right here. With a 0.6 water cement ratio, the compressive stress is about to the minimum amount required. Also, the recommend, I remember, is 12 megapascal at least.
All right. I had a question. I think it's on your next slide. Or a question about the additives. If they have such a negative impact on the hardness, what is commonly done to mitigate that?
Well, different additives have different purpose. Here, let's say the silica sand. If you add silica sand, yes, it drops the hardness, but it increases the thermal resistivity. Like the steel fiber, it increases the density of the cement.
Okay. All right. Any other questions?
Yes, the method we are using here is the Oliver and the Fast method. And the Young's modulus we're marrying, we're marrying is a whole system, including the cement and the additives. Actually, when the indenter tape contact with the additives, it actually measures the additives Young's modulus. When it's contact with the cement, it measures the cement itself.
Any other questions? All right, thank you very much.
Thank you.